Hey guys, how you doing? I hope you're doing well. Thanks for coming back. I am going to be talking a little bit about concentrations today, and then we're going to stop doing math for a while. I'm sure some of you will be thrilled to hear that we're not going to be doing math for a while. We're going to be doing something entirely different. It's all visually based and conceptual, so that it will be a nice break from all the math that we've been doing. Then we're going to take the second exam, and then we'll come back into some more mathematical things for our last set of stuff that we're going to do. So we're going to talk about concentrations. Now, concentrations are an important part of what we have to do, and we've seen some of this already. So we've talked a little bit about molarity. So we'll need to talk about molar concentrations. Molar concentrations are our most common way of dealing with concentrations. So that's moles per liter, and we'll talk more about that. We'll talk about dilution of solutions because it is an important part of what we talk about. It is something that gets mentioned often when you go searching on the internet, but it is not the right way to do everything. So it gets mentioned and they act, I often hear it spoken about as if it is the right way to do everything, but it is not. Okay, so we have to be careful how we deal with those calculations. We'll talk about gravimetric analysis, which is a very common way for us to analyze solutions that we're dealing with to see what their concentrations are. And then we'll talk about titrations, what they are, how we standardize things, how we talk about the difference between an equivalence point and an endpoint, what an indicator is and what we use it for, and how we do the calculations that are associated with titrations. Okay, we'll talk about why we do them, what those calculations are, what we need them for, and why they're done so often. Okay, so those are very, very common things to be done in a laboratory. And I mean, unfortunately, they're done everywhere. So it's an important thing to talk about. So questions, comments, problems on where we're going. Okay. So let's take a little bit of a look at where we've been. So I have 5 grams of water in 4.63 liters of ethanol. So what's my solvent? Now remember, and what's my solute? And is this an aqueous solution? Now remember that our definitions, my solvent is the thing that is present in the largest capacity. So my 4.6 liters is way bigger than the 5 grams. So that means my ethanol is my solvent. My solute is the water, because it's the smaller thing. And that means that this is not an aqueous solution. It would be an aqueous solution if the water were my solvent. So H2O is not the solvent. So this is not an aqueous solution. Okay. The only time it's aqueous is if water is the solvent. Okay. It is that simple. So it's all based on those definitions that we have, right? So now I want to look at 2 different things, HCl and CH3COOH. One of those is a strong electrolyte. Which one? My answer is going to be HCl. And I say that because we have HCl. It can dissociate. And remember, when we did this, we got H plus and Cl minus. And we had CH3COOH. And we got CH3CO minus plus H plus. And they're very similar looking equations. But remember, we wrote these differently. And this one had a single-headed arrow indicating that it only goes this direction. This one had a double-headed arrow indicating that it goes both directions. And so this was a weak electrolyte, only partially happens. This was a strong electrolyte, and that means it goes completely to that side. Okay, so this is the one that's the strong electrolyte. So HCl is my strong electrolyte. Now we have CaNO32 and NaOH. We want to talk about this reaction. So first thing, what are my products? So remember, we're going to do-si-do. So we have Ca, we'll go with the OH because we're going to trade the partners. So this positive goes with this negative, this positive goes with that negative. So I'm going to write this down here because it makes my life easier if I do. It's easier for me to follow what I'm doing when I do that. So Ca2 plus goes with this OH minus. I'm going to need to put two of those together. And I don't know why I wrote that there because I shouldn't have written it there. So I have that Ca2 plus, the OH minus here. So I need to have CaOH2 to be able to get that balanced. So that's my Ca and my OH. And then I'm going to have Na, and of course this is Na plus because he's in that first column. So remember from our periodic table, he's right here. So he's Na plus, and of course that NO3 minus is right there. So he's an NO3 minus 1, so it's a 1-to-1 relationship. NO3 minus, so NaNO3. And then, of course, if we look at our solubility rules and our solubility charts that we have information in here, don't do this to me. Okay. Hopefully that'll work. All right. Scrolling. Okay. So we look at this, and I look at my NaNO3. And remember, all common compounds of group 1 metal cations, so Na is in that, and all common compounds of NO3 minus are soluble. So this is going to be soluble, so this is going to be listed as aqueous. That is not my problem. If we look at CaOH2, so we need to come down here and see if we can find Ca. I don't find him listed here. So we come down here and we look at the OH, right? Compounds of hydroxide of group 1 cations, soluble exceptions, Ca2 plus. So this is also aqueous. So my two products should be CaOH2 and NaNO3. Are those products soluble? Yes, both of them are. So my net ionic equation for this is nothing. So no reaction because everything is soluble. So I have no net ionic equation for this because nothing forms a solid. So that's my answers for what we're talking about there. And that's because nothing forms a solid. Right? So, and what you would see if you look at this is that there's slight solubility for this CaOH2. So if you chose to write it, you could go, okay, well, the CaOH2 is slightly soluble. So the Ca2 plus aqueous plus the 2OH minus aqueous goes to CaOH2 solid could be the net ionic equation that you write for this because it is the only thing that has slight solubility issues. CaOH2 slightly soluble. And again, I see that because I see that right here in the table. But that's not what I see based on these rules. So it depends on where you look at that. You see it. Okay. So either one of those would work. Based on the rules, I wouldn't have seen that. Based on what's here in the table, I do see it, and so I could write this down. Either one of those would be an acceptable response. Okay. I'm going to pause for just a moment. Okay, sorry about that. I got an email from my boss that I need to deal with. I apologize. Okay, so those are our review questions. Any questions, comments, problems about anything that we talked about there? So that's a review on our aqueous solutions and our solubility. Okay, so let's talk a little bit about concentrations. So when we talk about concentrations, we are typically talking about how much of something is in something else. So we often talk about concentrations in terms of molarity, moles per liter. And so we symbolize that with a big M, and that is moles per liter. Okay. We can also talk about this in other terms. We can talk about it in terms of grams per liter. That is another way that we talk about this. We can talk about it in terms of trying to think of other things that we typically use, and my brain is completely blanking on me because I'm old. So I'm sorry about that. But those are, these are some other things that we will talk about a little bit later on when it is more relevant, because we need other units to deal with this when we talk about some other things. And so when we get into test 3 material, when we need those things, we'll talk about them. And there may be some mention of it in a couple of slides, so we'll talk about it. Okay. Our concentrations are an intensive property. It's not dependent on how much of the solution is present, because no matter what type of sample I take, no matter how much of it I take, that concentration stays the same. Now that's true for the amount of solute originally dissolved in a given volume. If I change that volume, if it either goes up or it goes down, either add more water to it or that water evaporates, then that has changed that concentration. Okay, so that's a problem. Right, so evaporation changes that concentration, and addition of water changes that concentration. So we need to make sure that we're not doing either of those things, because that will change what we're looking at. It's fairly easy for us to figure out what happens if we add additional water to it, because we can usually quantitate the amount of water that's been added, but it is very, very difficult for us to quantitate how much water has been evaporated from that solution. And so it's very difficult for us to figure out how that concentration has changed without doing some analysis on that solution. It's fairly easy for us to just look at a solution in a particular volumetric system to be able to say, oh, wait, we did this, all right? Now, when we make these solutions, what we typically do is we measure out an amount of solid, and then we add a volume of water to it, okay? The process of doing that usually heats that water. The dissolution of that solid into that solution usually heats the water, because it's a very favorable process. Okay, going into that water is very favorable for that solid, so it gives off a lot of energy when it does so. And so it's and when it does so, it gives off a lot of energy, and so it expands the water. And so we've got to be very careful about how we do that, because when that expansion happens, we've got to make sure that we haven't gone past the marcation on the volumetric container that we're using to make this thing. Because if we do that, then the mass per volume that we're trying to get will be violated. Okay, so we've got to make sure that we dissolve it and give it time to expand before we fill it up to that final volume. Okay, so there are some details in your textbook about how this works and how we put it in there and we mix it and we give it time to rest before we go ahead and do this. And typically what we like to do is put it in there, mix it, and let it cool back down to room temperature, and then fill it to the final to make sure that we've given it time to settle out is typically what we say. Settle out, make sure that it's actually where it's supposed to be, okay? So we've given it the time to expand the way it's supposed to, and it's come back to room temperature. So it's not going to contract on us while we're working with it. Right? So that's typically what we're talking about with that, okay? So our molar concentrations, again, moles per liter. And what that means for us is if we're working with a solution that has a concentration in moles per liter, we don't necessarily have to work with that in some of the same ways that we've talked about before. So when we've been working in our grams to moles to moles to grams, that's been our process in our stoichiometry. we have a situation where we're now in moles, but it's moles per liter. And so we now have to work slightly differently to get just to moles, because we now have to get rid of that volume. So we can take our moles per liter and multiply it by the volume in liters, and that'll give us the mole. So rather than going from grams and dividing by the molecular weight, we can take the moles per liter and times the volume, and that'll get us to mole. So it's a slightly different way of looking at the exact same thing. We're just starting in a different place. And so what you'll see here is that we can take the volume of a solution, A, in liquid, and use that molarity to get to the moles. Okay, so we can use the volume and the molarity to get to moles. We can then use that information in the molecular weight to get to grams. We can then use that information and Avogadro's number to get to the number of particles. We can then go from moles of A to moles of B. We can go from moles of B to grams of B. We can go from moles of B to the volume of B if we know the molarity of that solution. So we've now expanded what we can do by another dimension. Okay, so we've got another way to look at this. And of course, we don't have to do this the same way. So we could start with the solution over here and say, well, I use 20 milliliters of a 0.25 molar solution, and I want to know how much, how many grams of product I can make from that. And I can do that. That calculation is something I can do. I can take that volume, multiply it by the molarity, use the stoichiometric factor for my balanced equation, and then multiply by the molecular weight to get the grams. This is something that we do in the physical laboratory and something that you guys should be doing in the online laboratory to figure out how much of that product you've made. Okay? So that is something that we are working with in terms of how do we work with these numbers in this material. All right? So new things, more stuff, we can get to more information from our systems. Okay? Now, other units, other concentration units that we may run into. Okay. And this used to be the slide, where it came from, but that reference is not necessarily valid anymore. I apologize for that. But there are some other units that we do talk about, and percent by mass, we've actually already dealt with. So we can calculate the percent by mass by saying the mass of this particular solute over the mass of the solution times 100. Now, we dealt with this when we talked about in percent masses, when we were getting ready to talk about empirical formulas, right? So we could calculate a percentage of, say, carbon in carbon dioxide. So we could take the mass of the carbon divided by the total mass times 100. Percent by mass here is defined exactly the same way, except we're talking about the mass of the solute over the mass of the solution. Okay, same definition. We can talk about the molarity, which is the moles of the solute for the liters of solution. We just talked about this, and that's equal to big M. Okay. It is easier to measure, used to discuss solutions for titration and gravimetric analysis. This is typically what we're going to be talking about. We're talking about stuff in the laboratory. This is the most common unit that we use in the laboratory, grams and molarity. Those are our lab units. Okay. But there are a couple of other things that we talk about in the laboratory, one of which is called a mole fraction. Well, a mole fraction for component A is called chi A. This is a Greek chi, and that's the moles of A over the sum of all of the moles of all components. And it's used when we talk about the partial pressures of gases and the vapor pressures. Okay, it's a fraction of how much of this thing is from that component. So the total, I need to know how much of it is from this component, because then I can figure out what part of the pressure is from that component. And it's useful in talking about the pressures that way because we can, they're additive. So we can do that. All right. So that's one of the places that we'll see this. There are other places that we do want to talk about those fractions, and so that's where we'll see these fractions coming into play. Okay. So that's another place, another type of unit that we will talk about eventually. And that's all based in the ratio of the moles. And there's one more unit that we'll eventually get to, and that's called molality. Okay. Now, molality is defined as the moles of solute over the kilograms of solvent. Okay. And for reasons that are so ridiculous, it's insane, it is symbolized as small m, and it's italicized. So big M, small m, yes. Now we don't typically use this small m anymore. Alex will tell you that it's an antiquated unit, and we don't call it that anymore, and I understand that, but you know, as old folk will still do that, okay? So the reason that we use molality as moles over kilograms is because that does not change. So our volume, this liters, is dependent on the volume of that solution. And as the volume changes, you know, as the volume changes as the temperature changes. So as the temperature goes up, that volume goes up. Okay. So as the temperature goes down, the volume goes down, typically, you know, with assuming that we're in a water solution. Okay? It does some other things for other solvents, depending on what they are. So that becomes problematic because as we change the temperature, then we may see changes in our volumes. So for some things where we're trying to look at the effect of temperature on these solutions, or the effect that this thing is having on those temperatures, then we need something that's independent of that volume, right? So for certain measurements, we need to use something that's independent of that volume change. And so that's why we would use molality, because these kilograms, this here, this mass, is not volume dependent, okay? And so it's independent of the temperature change, okay? So moles of solute per kilogram of solvent, this is independent of temperature. And so it can be used where the temperature is changing and it doesn't change. So that's when molality becomes a thing. So it is a different unit. We do have these four that we talk about. We eventually go into how do we, you know, do calculations between them. And there are some calculations that we can do between the four of them. We will do that for the last exam. Okay. Now let's talk about something that, I mean, I love dilutions of solutions because we do these a lot. There are practical reasons why we cannot always make the solution that we need to make. So if I want to go into the laboratory and I want to make a very low concentration solution, I cannot directly measure that because there's only a finite way that I can measure things in the lab. I can't measure a really, really low concentration because that would require me to measure a really, really small mass or a really, really small volume, and I cannot do that. There are physical limitations to it. So that means that I have to make a higher concentration and then dilute it. Okay, and so I need ways to calculate what's the new concentration when I do the dilution, when I add water to it, what's the new concentration? And so we have some shortcuts for being able to do that. Because what happens when I do a dilution is I take one solution that has a given concentration and a given molarity, and it has a particular volume. And so if I multiply those two things together, it says I have this many moles of this material that are present in this sample. And then I add more water to it. So I have this many moles, I have a new volume, and so I have a new concentration. Okay. So in that case, we can use this M1V1 equals M2V2, where M1 is the original molarity, V1 is the original volume, M2 is the final molarity, and V2 is the final volume. Okay, and in that case, we know that, you know, the original molarity times the original volume is the number of moles. The final molarity times the final volume is the same number of moles. because I haven't added any more material to this. So it still has to be the same number of moles. Okay, so it has to be equal. Now, why can't I use this when we talk about some other things? When we're talking about stoichiometry and things like that? Because it doesn't take into account the molar ratios. And so, will this work sometimes? Yes, absolutely it will, if the molar ratios are the same. But it doesn't take them into account. And so it's a really bad idea to set yourself up to do math this way, because then you forget to take that molar ratio into account. And so when it's not 1-to-1, you forget to look at it. And that's why I don't do this, because it doesn't take that into account. And it's a really bad idea. It's a really bad habit to get into. Okay. So I do not recommend doing that. I would use this only for dilution of solutions and not for stoichiometry. That is my why. That is what I'm going to tell you. It is a bad idea. So I would not do that. So this works for dilution only. And that's the only time I want to see you using it. If you do it on a test for anything that is not dilution of solutions, I am going to flip out about it. And I don't use red pen on grading your stuff, although I could. There is a red font available to me, but I will not use it. But there will be a lot of don't do this, don't do it, don't do it. You know, that kind of thing is not. And there are reasons why we should not be doing it. And it's because we don't take into account that molar ratio, and that molar ratio is incredibly important. Okay. So dilution of solutions, original molarity, original volume, final molarity, final volume. And so we can find that final volume by taking that original molarity times the original volume divided by that final volume. So that will give us what we need to do. Okay. Now, concentration units. Again, we talked about percent by mass, mole fraction, molarity, and molal. We can do some calculations here to move in between them. I put this here, and we could do this right now. I don't necessarily think that this is the best place to do this. And so I'm going to actually skip this for now. I'm going to put up this answer for you guys, but I really don't think that this is relevant until exam 3. But I will put up this answer. Because I really don't think it's relevant until exam 3. I'm not sure why I moved it here. I know I had a reason, but I think that what it ended up doing is confusing people. And so I think I need to move it back to where I had it before. So I apologize for it still being here. Okay. So let's ignore it for the time being. And like I said, I will put up that answer and I will talk about it again when we talk about this topic in the Is my brain failing? Getting old really sucks. Freezing point depression. Colligative properties. That's the word I was struggling to find. Colligative properties lecture, which is like the next to the last lecture that we do. Colligative properties. That's where this used to fall, and we'll talk about it there. Okay. So, and again, exam 3. All right. So questions, comments, problems so far. Okay. Now we need to talk about titrations. So we've talked about what concentration is. It's moles per liter. We've talked about the fact that there are other concentrations units that we can use and that they're not really that relevant now. We've talked about the fact that, there are other things that we can do. We can dilute solutions and we can find out what that new concentration is once we've done a dilution. I haven't given you examples yet, but that is something that we can do. But we're going to talk about titrations, and we need to talk about titrations because you're going to be doing these in the laboratory, which is why we need to talk about this now. Titrations, in my opinion, are very awesome, and they're extremely useful for finding out information about the solutions that you're working at. We're going to start with acid-base titrations. There are many different types of titrations that happen. And we start with acid-base titrations because we know that acids and bases can react to give us salt and water. We talked about those reactions when we talked about aqueous solutions, so in the last lecture. And we can use that neutralization reaction to identify the concentration and the identity of something that we don't know. Okay? As long as the other material that we're dealing with has a very well-known concentration or composition, as long as we don't know what that other, so if we have an unknown in this beaker, but I have something in here, this is a burette. As long as the thing in that burette is very well known, I can use the relationship between these two when I react them together to figure out stuff about this unknown. So one, how much of it takes to react will tell me stuff about what the concentration is. It can also tell me whether or not it's a single proton or multiple protons or single base or multiple bases, okay, depending on whether we're having to titrate in an acid or a base. Okay, I can figure those things out. And that composition of the curve, what it looks like when I titrate it, can tell me, is it a single proton or is it multiple protons, those kinds of things. And those things are very useful to me, okay, because it can help me to narrow down what I might be looking at. Right? Other things that these curves can tell me is based on where those some of these transitions happen, it can help me to narrow down what those acids and or bases can be. Right? So these are extremely useful things that we can do to help us identify what is in that beaker. Right? So as long as we know a lot about this solution, then we're good. But we may need to do some testing against this solution to know some stuff about it. And that process is called standardization. So we're going to talk about what it means to standardize. We're going to talk about how we get to that process. And then we can talk about how we use that standard to learn things about our own. Okay? So when we want to know about an unknown acid, we have to react it with a base that is very well known. But most of our bases are not that well known. They're not that stable. And so we have to get them to a point where we know a lot about them. And in order for us to do that, we have to react it against something that is extremely stable. Something that we know that is extremely stable, that is an acid, a primary standard, is KHP. So KHP is potassium hydrogen phthalate. That's what that stands for. And potassium hydrogen phthalate is a very well-known composition. So KHP actually looks like this. It's KHC8H4O4. It has a molar mass of 204.2 grams per mole. It is monoprotic, so there's one proton, this one right here, that's on it, that can be reacted with this NaOH. Okay, so if I'm reacting it against NaOH, there is one proton that can do that reaction. And then we get left with all of this other stuff. And so this is an ionic equation for that process. Okay. So that is the reaction that we can see when we work with this standard. Now, KHP is extremely stable. It doesn't react with water. It doesn't pick up water anywhere. It's not hydroscopic, meaning that it picks up water. It's not temperature sensitive. It doesn't do a lot of things in the atmosphere. So it's very easy for us to work with. NaOH, when it's sitting in a container, can react with CO2 from the atmosphere, and that changes its composition within that container. And so it can be difficult to know exactly what we're dealing with when we go and make that solution. It may not be exactly the composition that we think it is. And that's why we have to standardize. Okay. So some things are reactive as they sit in the atmosphere. And so we have to make sure that we know what we're dealing with. So we react the NaOH against the KHP to make sure we know what its concentration is at the time we're using it. So we standardize it first. So we're going to take 5 grams of KHP. We're going to add it to a volumetric flask and prepare 25 milliliters of that solution. The first thing I have to know is what is the concentration of the KHP in the flask? Okay, so that's my first question. All right, well, I want a concentration. So my concentration units are what again? Concentration units are moles per liter, which is big M. So molarity, big M, moles per liter. All of those are the same thing. Let me actually make that legible. It's a big M, and then it's molarity. So those are equal to each other. That's what all of that means. So if I want to take this KHP and this volume and turn that into a molarity, I have to take that 5.000 grams of KHP and divide that by the molecular weight of KHP. Now, back here, I said that the molecular mass of KHP was 204.2 grams per mole. I know that because the bottle in the laboratory says exactly that. Now, could I calculate that? Yeah, absolutely, because you've got this formula right here. So I could calculate that that is 204.2 by taking and adding potassium and this hydrogen and these 8 carbons and these 4 hydrogens and these 4 oxygens. If I added all of that together, I would get 204.2. Okay. Now it depends on which table I use, exactly what I'm going to get. You know, I've seen some of those variations, but that bottle says 204.2 grams per mole, so that's what I'm going to use. Include the KHP, just so I know what I'm talking about. Cancel out my grams of KHP, and I'm left with moles of KHP. Now I'm in moles. I need to divide by the volume, so I have 1 over 25.00 milliliters. I don't want it in milliliters, so I'm going to take 1,000 milliliters per 1 liter. And I do all of this happy math. If I do all of that happy math, divided by 204.2 divided by 25 times 1,000, that gets me 0.9794. And I have that as 4 sig figs because this number right here has 4 sig figs. This also has 4, although we don't use that to determine our number of sig figs. This has 4 sig figs. So both of the numbers I was given in my starting thing have 4 sig figs. So my answer should have 4 sig figs. Zero 0.9794. And that's mole. Try and make that a little more legible for you. So that's the molarity of the KHP. The KHP 0.09. Put a 0 in there, it does belong there, 0.9794. Okay. Now it says I prepare 49.326 grams of NaOH in a total volume of 1,000 milliliters to do a titration. Reacting this solution against the KHP, I find that a sample of 50 milliliters of the NaOH requires 49.624 milliliters of KHP to reach the endpoint. What's the theoretical molarity of the NaOH? What's the actual molarity of the NaOH? And what's the percent error of the molarity? Okay. So I need to find theoretical molarity, and actual molarity, and a percent error. So a couple of questions for you guys. What is the difference between theoretical and actual? My theoretical is based all in calculations. Okay, so that's my theory, is based all in calculations. So that's the stuff on paper. My actual is based on what I found in the lab. So what I found in the lab is that this amount of NaOH requires this amount of KHP, right, to reach the endpoint. So that is my actual that I worked with. All right. So this is my actual that I'm dealing with there. And my theoretical molarity is going to be based on what this would give me. So this mass divided by this volume is going to give me a molarity of NaOH. This volume and this molarity will be able to give me a molarity of NaOH through calculation. And that will give me my theoretical molarity. And then I can calculate a percent error by looking at the difference between the two. So let's talk about how we do that. The first thing I need to do is to calculate what I think the molarity of the NaOH should be based on the information that I was given here. So I have 49.326 grams of NaOH. I should convert that to moles. And in order for me to do that, I need to look at the molecular weight of NaOH. So I'm going to scroll up and look at the mass. I'm actually going to pull up this table right here. And I find my sodium is 22 point, somewhere around there, 22.99. Plus 15.999, if I'm not mistaken. 994. No, actually, sorry, 15.999. Plus 1.008. So 39.997. 39.997 grams of NaOH in 1 mole of NaOH. And then that is in 1,000 milliliters, which is 1 liter. And so I do that happy math, 49.326 divided by the number that I just calculated. And that gives me 1.2332 mole NaOH. And this is based on theory, so this is my theoretical. Okay, so that's my theoretical value. Now, my actual is going to be based on the titration that I did against the KHP. So I need to look at this reaction that I did. So I reacted KHP plus NaOH. And when I did that, I end up with an NaKP plus H2O. I know that looks really weird, but that's what's left. So if I take out this H that reacted with the OH here, because that's what happens, I'm left with the KP plus the Na. That's what that looks like. Okay. And we talked about this before. So we actually looked at this here. Okay. We left off the Na when we did this, but this is the P, right? We left off the K and we left off the N and the NA right here. So there's no K listed here. No K listed here, no NA listed here. So neither one of them is included. That H is right here. So we yank that H off of here, it goes to the OH right here, that makes the H2O. And then this thing that we're calling a P is right there. Right? That's what that looks like. So we're calling it P. And it's called P because it's phthalate. That's what they call it, is phthalate. Okay. So, and again, if we wanted to put the counter ions on this, we have a K that goes here, an Na that goes there. And so we would end up over here with an Na plus K plus, and then that guy. And that's how we get this answer that we're talking about there. So it's NaKP. So that's where that counter part comes from, this NaKP. Again, didn't include it here because we were looking at just an ionic equation that has the relevant parts in it. Okay, so we could have left this out, but we didn't. Told you, sometimes we do crazy things and include stuff that is only the parts that we think are important. And at this point, they thought that the phthalate was important. So, all right, so here's my theoretical. Now, I wrote this equation because this is what actually happened. And so I know that 50 milliliters, I'm sorry, at 50 milliliters of NaOH reacted with 49.624 milliliters of the KHP, which again had that 0.9794 molar concentration. We calculated this before. So I know that all of that information is true. Now, I need to figure out what the concentration is here. That's what I'm looking for. That concentration is the experimental value that I need to know, the actual molarity. That's what I'm looking for. So in order to find that, I need to start with what I know the most about, this. And I always start with the volume because it's by itself. It only has that one unit. So I start with this 49.624 milliliters. I do a unit conversion, 1,000 milliliters per liter. And I do that because I then want to multiply it by the molarity, 0.9794 moles of KHP per liter. Liters will cancel, the milliliters will cancel, and I'm left in moles of KHP. That's the unit that I have left. I don't want to be in moles of KHP. I want to get rid of that so that I can get to moles of NaOH, right? Because that's what I need to know about. But I know it's a one-to-one relationship. I know that 1 mole of KHP reacts with 1 mole of NaOH. So I've canceled my moles of KHP and I'm now in moles of NaOH. In order to get to a molarity, I need moles per liter. The only other thing I know about this is that I had 50 milliliters here, right? So I can, me, being me, I'm just going to put that it was a 50 milliliter sample down here. And then I can do a unit conversion. I know that there's 1,000 milliliters, and I, of course, never put it in this room. 1,000 milliliters in 1 liter. So the milliliters will cancel there, and that will leave me with moles over liters over liters, because everything else is canceled. And so let's do that happy math. 49.624 times 0.9794 divided by 50 times that. Divide by 1,000 too. We need to get rid of the 1,000 that was right here. So these end up canceling each other. So we really don't need to include them. If we choose not to, that's okay. But that drives my head crazy. So, and that gives me 0.9720. And looking at what I have 5 sig figs there. I have 6 sig figs there. I have 5 sig figs there and 2 right there. So in theory, this should actually only be reported to 0.97 molar. NaOH, and that's my actual. So this is what we thought it would be, theoretical. This is what it actually is. It's a pretty big difference, isn't it? And again, this is what we were talking about. So on the bench, when this jar of NaOH was sitting there, it was reacting with CO2 from the atmosphere. And so a lot of it has reacted with that CO2 from the atmosphere, and it's gone away. It's changed. So we have a big difference. Now, if I want to look at the percent error, that's going to be equal to the absolute value of the theoretical minus the actual. I shouldn't have written that part yet. Over the theoretical times 100. I take percent error is equal to 1.2332 minus 0.97 over 1.2332 times 100. And that gives me 21. And again, 2 sig figs in this number right here. So that leaves me with 2 sig figs in my answer. 21% error. And it is what it is. You know, I mean, the error is high, yes, but that is what I have found. So there's not much I can do about it. It's not my fault that it did what it did. It did what it did. I can't really do anything about it now. Now, can I say, yes, this made a boo-boo, and we shouldn't have done it like that. I can't be accusatory about that, of course, but I can say, perhaps we need to store this differently and come up with some solutions for how we could store this so that it wouldn't be a problem. Coming up with solutions is always good. Okay, so that's what we're talking. We have now answered all of the questions that we've been given about this particular scenario. I standardized my NaOH against the KHP, found my theoretical molarity of NaOH. I have my actual molarity of the NaOH and my percent. Okay. Now, when we talk about titration calculations, just I can do mass calculations using moles. I can do the mass to reactant moles using the molecular weight. I can do the concentration using that moles per volume. Eventually we'll get to this volume. That'll happen after we do our next, in the next test. So it'll be right after the next test. We'll do this part. So mass and concentration, we've now talked about both of those. So our stoichiometric map has grown. So I can get to reactant moles, use my balanced equation to get to product moles, and now I can go to mass and concentration over here. And again, that's in this table. I go over here, right here. So I've now added this part to the table. We had this part, we had this part, now we've added this part. So we've added to our gamut of things that we can do. Okay? All right. Questions, comments, problems about what we've got? Okay. So let's try some more calculations. I have a 25 milliliter sample of 0.50 molar NaOH. It's titrated until neutralized in a 50 milliliter sample of HCl. What's the concentration of HCl? Okay. Very first thing I need to do is balance my equation. So let's write a balanced equation for this. I'm reacting NaOH and HCl. I get NaCl. That's the salt that comes out of this. And I get H2O. So that's my balanced equation. I have a 25 milliliter sample, 0.5 molar NaOH. So 25 milliliters, 0.50 molar. And I have a 50 milliliter sample. And I don't know what this concentration is, but I'm looking for it. So this is what I've got to work with. Notice I've taken all of that information out of this question, and now I can work with what I've written down here. I start with what I know. I always start with what I know the most about. And I always do the volume first, 25 milliliters. Do my unit conversion, 25 milliliters, 1,000 milliliters per 1 liter. That cancels my milliliters. I know that my molarity is in moles per liter, so I have 0.50 moles of NaOH in 1 liter, so that cancels the liters. I know I have 1 mole of NaOH and 1 mole of HCl. Now, I'm going to take an opportunity to slow down here for just a second. And I want to talk about this because when I was saying that we don't do our stoichiometry using that M1V1 equals M2V2, notice that what I've done here is the V1 times the M1. I have. But that didn't, and I said, we don't take into account that stoichiometry. What I wouldn't have included was this step right here. Now here it doesn't matter because it's 1 to 1. So I'm just multiplying by 1, so it doesn't matter, right? But this is the step that I need to make sure that I've included. And that means I need to look at this equation to make sure that 1 mole of NaOH reacts with 1 mole of HCl. And I know that because I have canceled out the moles of NaOH by putting it down here and putting that number in front of it. And I've converted to moles of HCl, and I put the number in front of that. And I do that because I write this unit and then look at the number. I write this unit and then look at the number. If I leave this step out, if I don't build this into my process, then I don't know that I've considered this every time I do this. And so this V1 times M1 is equal to V2 times M2, or I just do the divided by V2 over here, and that's supposed to equal to the M2, then I haven't taken that into account. And that's what bothers me about people using this to try and answer these questions. Because you haven't taken this part into account. And again, if we're doing a 1-to-1 ratio, it does not matter. But we don't always do that. Okay. And I can guarantee you that I will put one of these on the test to make sure that you are thinking about it. That is a guarantee, because I want to make sure that you understand what the implication is to balancing that equation. Right? So, and I'll stop talking about that and I'll get back to this. So we've now gotten rid of the moles of NaOH when we're in moles of HCl. And we want moles per liter. So we need to divide by that volume that we have for the HCl. And it's 15 milliliters. So I just put 1 over that 15 milliliters. And this is just a placeholder. And so that's why I have the 1 there. It doesn't mean anything. It's just to hold that space. I know there's 1,000 milliliters in 1 liter. So milliliters cancel. I have the liters on the bottom, and I have moles per liter. So I can do that happy math. 25 divided by 1,000 times 0.5 divided by 50 times 1,000. I end up with 0.25. Now, looking at my numbers that I have, 2 sig figs, 2 sig figs, 2 sig figs, so 0.25 molar is appropriate. And that's 0.25 molar HCl. And that makes sense to me. In my head, if I look at the numbers that I've got, it's a 25 milliliter sample of NaOH, which is 0.5 molar. This is a 50 milliliter sample of HCl. So I would expect that if it takes 50 or 25 milliliters of a 0.5 molar, and I have a 50 milliliter sample here, then it should be half the concentration. That makes sense to me, because it's a 1-to-1 ratio between the two of them. So it should be half the concentration if it requires twice as much. Okay, so that's what, or half as much of this to do. Okay. Questions, comments, problems on the work that we did there. So I'm going to let you set this one based on what we've done already. And I'm going to come back in just a few minutes to see what you did. Okay, so I set this up much like I did before. I had 83 milliliters of a 0.45 molar NaOH. So I put that here. 235 milliliters of the HCl. I want to know what that molarity is. So I had my 83 milliliters. I convert that to liters. I multiply by the 0.45 molar. I have my mole-to-mole ratio. I have my 1 over the 235 milliliters. And then, of course, I convert that to liters. And that gave me 0.16 molar HCl. So it's, pretty much the same thing. Math was a little messier, but of course I was trying to make it a little bit harder as we went on. So there you go. Questions, comments, problems on doing our calculations. The idea here is that we set up a process to do this. We pull the information out of that question, we set it up the same way every time, and then it should be the same process every time. I want you to get in the habit of trying to do it this way. This is the same kind of process that we were using when we were trying to do it with the masses. I was trying to set you up like this. And so as we continue, I want to see us setting up this same process for everything. Because if we're doing it this way and we're saying, okay, I'm going to put any information that I have around this thing. And so when I have a mass, I put the mass up here, and I need a molecular weight down here. When I have a volume, I put the volume up here, and then I put the molarity down here because it gave that to me. I put whatever I'm looking for, the unit that I'm looking for down here, and then I just put the information that I have into these brackets, and I go, okay, this is where I am. I don't want that unit. Let me convert it. I have this. Let me convert, this unit. I want to get rid of it. Let's convert it. I have this unit. I don't want it. Let's convert it. And this, okay, I do want that unit, but I'm not entirely done yet because I have moles, but I need moles per liter. So how do I get from here to where I need to go? And that's the way my head works when I'm trying to work through this is how do I, where am I? Where do I need to go? And how do I get from here to there one step at a time? And I'm trying to set all of these things up in as repetitive a fashion as I can, because then I don't have to think about it. It's just, okay, break it down. What did they give me? What are they asking me for? And how do I get from here to there? And if I can make that as rote and routine as possible, then maybe I have a chance of answering these questions. Because I don't have to necessarily sit and overthink, what are they asking? I can just sit down and say, okay, what did they give me? What don't I have? How do I get from here to there? And, like I've said, I really didn't understand anything about my physics class, but I knew how to take these numbers that they gave me, put them around some of the information that I knew about physics and, some relationship that I had, and go, okay, this is the one thing I don't know anything about. So I'm obviously needing to go there. How do I get from here to there? And may not be the best way because it may not actually get me to understanding the information. But as I continued to build these equations and build these relationships, I started to understand what it was that I was trying to do. And for me, that worked. Not only did it get me the answer that I needed, but it helped me to understand what I was doing and why I was doing it. So I'm hopeful that that will click for you as well. As you continue to be able to move through this, you'll start to see that there's connections. Oh, this goes with this, this goes with this, this goes with this. Oh, okay, I get it. That's the kind of thing that we're hoping. Right? But I am trying to set you up with a system for how we approach these problems. Okay? So those are some of our calculations. Now, we have some more standardizations that we need to do. So we're going to go back through this again. And then we're going to go through the whole thing one more time. Now, I'm going to set this, set you here and say, I want you to do this. I want you to try this one on your own because we've already done it. So I'm going to pause here, stop this video, make a gap in this one, and set you up with a new video. And then I'm going to come back and I will make another video for the rest of this slide set. Okay? I will talk to you guys soon. Thanks.